For billions of years, a celestial ballet has unfolded right here in our cosmic backyard. 8 magnificent planets, along with countless asteroids and comets, dance around our sun in seemingly perfect harmony. Day after day, year after year, they trace their paths with astonishing precision. Have you ever wondered why, amidst all this motion, these colossal bodies don't simply collide in a spectacular, system-ending It's a question that, at first glance, might seem obvious, but the answer is a fascinating blend of physics, cosmic history, and a touch of gravitational. Imagine a bustling highway, but instead of cars, you have planets, each one traveling at mind-boggling speeds. Instead, they largely stay on their own designated lanes. And what about those lanes? Each planet has its own unique orbital distance and speed. Mercury, the closest, zips around the Sun in just 88 Earth days. Neptune, the farthest major planet, takes a leisurely 165 Earth years to complete a single lap. You'd expect chaos, right? Yet, in our solar system, collisions between major planets are extraordinarily rare. It's like having multiple runners on a circular track. As long as they stay in their lanes and maintain their rhythm, they won't bump into each other. If there was still a huge amount of leftover material in their paths, collisions would be far more common. It's the Sun's powerful gravity, perfectly balanced by each planet's momentum. It's the initial conditions that flattened our solar system into a disk. It's the subtle, stabilizing dances of orbital resonances, and it's the long, slow process of each planet carving out and maintaining its own cosmic path. Dwarf planets like Pluto, for instance, haven't cleared their neighborhoods, which is one reason they're classified differently. Our major planets have done the heavy lifting, establishing their dominance and maintaining their clear highways. Sometimes, the gravitational tugs between planets can create fascinating, stable patterns. They prevent orbits from becoming too eccentric or from significantly changing their tilt, which could otherwise lead to more frequent close encounters. Intricate arrangement is a testament to the laws of physics and the incredible resilience of our solar system. It allows for the sustained conditions that have, for billions of years, made life possible on at least one of these perfectly placed worlds. The cosmic dance continues, silent and magnificent, a constant reminder of the profound order hidden within the vastness of space. This isn't just about avoiding collisions, but about the very definition of a planet itself. One of the criteria for being a planet is that it must have gravitationally cleared its orbital path of other significant debris. Think of it as a cosmic over billions of years. The planets have either accreted or ejected most of the smaller, rogue objects from their orbital zones. Imagine 2 planets where one completes exactly 2 orbits in the same time it takes the other to complete one. This creates a rhythmic, predictable interaction that can actually stabilize their orbits over vast. It's like cosmic choreography, where the dancers naturally adjust their steps to avoid treading on each other's toes. But on a cosmic scale, gravity is the grand architect, the conductor of this planetary orchestra. This delicate balance between the inward pull of the Sun's gravity and the planet's forward momentum is precisely what creates an orbit. Think of it like this. If you swing a ball on a string, the string pulls it in, but the ball's motion keeps it from falling directly to your hand. If you cut the string, the ball flies off. Our planets are doing something similar, but with an invisible, immensely strong string made of gravity. It's the powerful, invisible hand of our sun that keeps every planet locked in its embrace. Without the sun's immense gravitational pull, our planets would simply fly off into the cold, dark void of interstellar space. The key lies in understanding a few fundamental principles that govern the cosmos. At the heart of it all is gravity. We often think of gravity as the force that keeps our feet on the ground, or an apple falling from a tree. Each planet is in a perpetual state of falling towards the sun, but it's also moving sideways at incredible speeds. Beyond gravity, there's another crucial factor, the orbital plane. When our solar system was born, about 4.6 billion years ago, it began as a vast, rotating disk of gas and dust. As this disk spun, gravity pulled most of the material into a central star, our sun. The remaining material flattened out into a thin disk, much like pizza dough being spun. This primordial disk is why all the planets today orbit the sun in roughly the same flat plane, almost as if they're racing on a colossal, multi-lane racetrack. This flat arrangement dramatically reduces the chances of head-on collisions. It means planets aren't randomly zipping up and down. crossing each other's paths willingly. Because their orbits are distinct and planets rarely even come close enough for their gravitational pulls to significantly destabilize each other in the short term. But the story doesn't end there. There's an even more subtle layer of order at play: orbital resonances. While not all planets are in perfect resonance, these gravitational relationships help to maintain the long-term stability of the solar system. And finally, there's the concept of clearing the neighborhood. This process is why the space between the major planets is relatively empty. So, the reason our planets don't routinely crash is not by sheer luck, but by an elegant combination of forces and historical processes.